In geometry, a pentagon is any five-sided polygon or fivegon. The sum of the internal angles in a simple pentagon is 540 degrees. A pentagon may be simple or self-intersecting. A self-intersecting regular pentagon is called a pentagram. Regular pentagons. A regular pentagon has Schläfler symbol 5, and interior angles are 108 degrees. A regular pentagon has 5 lines of reflectional symmetry, and rotational symmetry of order 5. The diagonals of a convex regular pentagon are in the golden ratio to its sides. Its height and width are given by where r is the radius of the circumcircle. The area of a convex regular convex pentagon with side length t is given by a pentagram or pentangle as a regular star pentagon. Its Schläfler symbol is 5 halves. Its sides form the diagonals of a regular convex pentagon. In this arrangement, the sides of the two pentagons are in the golden ratio. When a regular pentagon is inscribed in a circle with radius r, its edge length t is given by the expression, and its area is, since the area of the circumscribed circle is the regular pentagon fills approximately 0.7568 of its circumscribed circle. Derivation of the area formula. The area of any regular polygon is, where p is the perimeter of the polygon, and r is the inradius. Substituting the regular pentagon's values for p and r gives the formula with side length t. In radius, like every regular convex polygon, the regular convex pentagon has an inscribed circle. The apothegm, which is the radius r of the inscribed circle of a regular pentagon, is related to the side length t by chords from the circumscribed circle to the vertices like every regular convex polygon. The regular convex pentagon has a circumscribed circle. For a regular pentagon with successive vertices a, b, c, d, e, if P is any point on a circumcircle between points B and C, then P plus PD equals PB plus PC plus P. Construction of a regular pentagon. The regular pentagon is constructible with compass and straight edge, as 5 is a Fermat prime. A variety of methods are known for constructing a regular pentagon. Some are discussed below. Richmond's method. One method to construct a regular pentagon in a given circle is described by Richmond and further discussed in Cromwell's polyhedra. The top panel shows the construction used in Richmond's method to create the side of the inscribed pentagon. The circle defining the pentagon has unit radius. Its center is located at point C and a midpoint M is marked halfway along its radius. This point is joined to the periphery vertically above the center at point D. Angle CMD is bisected, and the bisector intersects the vertical axis at point Q. A horizontal line through Q intersects the circle at point P, and chord PD is the required side of the inscribed pentagon. To determine the length of this side, the two right triangles DCM and QCM are depicted below the circle. Using Pythagoras' theorem and two sides, the hypotenuse of the larger triangle is found as side H of the smaller triangle, then is found using the half-angle formula, where cosine and sine are known from the larger triangle. The result is, with this side known, attention turns to the lower diagram to find the side S of the regular pentagon. First side R of the right-hand triangle is found using Pythagoras' theorem again. Then S is found using Pythagoras' theorem and the left-hand triangle is. The side S is therefore a well-established result. Consequently, this construction of the pentagon is valid. Carlyle circles. See main article. Carlyle circle. The Carlyle circle was invented as a geometric method to find the roots of a quadratic equation. This methodology leads to a procedure for constructing a regular pentagon. The steps are as follows. Draw a circle in which to inscribe the pentagon and mark the center point O. Draw a horizontal line through the center of the circle. Mark one intersection with the circle as point B. Construct a vertical line through the center. Mark one intersection with the circle as point A. Construct the point M as the midpoint of O and B. Draw a circle centered at M through the point A. Mark its intersection with the horizontal line as the point W and its intersection outside the circle as the point V. Draw a circle of radius OA and center W. It intersects the original circle at two of the vertices of the pentagon. Draw a circle of radius OA and center V. It intersects the original circle at two of the vertices of the pentagon. The fifth vertex is the rightmost intersection of the horizontal line with the original circle. Steps 6 to 8 are equivalent to the following version, shown in the animation. 6a. Construct point F as the midpoint of O and W. 7a. Construct a vertical line through F. It intersects the original circle at two of the vertices of the pentagon. The third vertex is the rightmost intersection of the horizontal line with the original circle. 8a. Construct the other two vertices using the compass and the length of the vertex found in step 7a. Using trigonometry and the Pythagorean theorem the construction, we first note that a regular pentagon can be divided into 10 congruent triangles as shown in the observation. Also, cos 36 degrees equals. In step 1, we use 4 units and a right angle to construct a segment of length 1 plus square root 5, specifically by creating a 1 to 2 square root 5 right triangle and then extending the hypotenuse of square root 5 by a length of 1. We then bisect that segment, and then bisect again, to create a segment of length. In step 2, we construct two concentric circles centered at O with radii of length 1 and length. We then place P arbitrarily on the smaller circle, as shown. Constructing a line perpendicular to O passing through P, we construct the first side of the pentagon by using the points created at the intersection of the tangent and the unit circle. Copying that length 4 times along the outer edge of the unit circles gives us our regular pentagon. Proof that cos 36 degrees equals let U equals cos 36. First, note that 0 less than U less than 1. Now, this follows quickly from the knowledge that twice the sine of 18 degrees is the reciprocal golden ratio, which we know geometrically from the triangle with angles of 72, 72, 36 degrees. From trigonometry, we know that the cosine of twice 18 degrees is 1 minus twice the square of the sine of 18 degrees. And this reduces to the desired result with simple quadratic arithmetic. Another method is this. Draw a circle in which to inscribe the pentagon and mark the center point O. Choose a point A on the circle that will serve as one vertex of the pentagon. Draw a line through O and A. Construct a line perpendicular to the line OA passing through O. Mark its intersection with one side of the circle as the point B. Construct the point C as the midpoint of the line OB. Draw a circle centered at C through the point A. Mark its intersection with the line OB as the point D. Draw a circle centered at A through the point D. Mark its intersections with the original circle as the points E and F. Draw a circle centered at E through the point A. Mark its other intersection with the original circle as the point G. Draw a circle centered at F through the point A. Mark its other intersection with the original circle as the point H. Construct the regular pentagon AEGHF. Side length is given the regular pentagon according to the golden ratio. Draw a segment AB whose length is the given side of the pentagon. Extend the segment bar from point A about 3/4 of the segment bar. Draw an arc of a circle, center point B, with the radius AB. Draw an arc of a circle, center point A, with the radius AB. There arises the intersection F. Construct a perpendicular to the segment AB through the point F. There arises the intersection G. Draw a line parallel to the segment FG from the point A to the circular arc about point A. There arises the intersection H. Draw an arc of a circle, center point G with the radius GH to the extension of the segment AB. There arises the intersection J. Draw an arc of a circle, center point B with the radius bj to the perpendicular at point G. There arises the intersection D on the perpendicular, and the intersection E with the circular arc that was created about the point A. Draw an arc of a circle, center point D, with the radius bar until this circular arc cuts the other circular arc about point B. There arises the intersection C. Connect the points B, C, D, E, A. This results in the pentagon. The golden ratio Euclid's method. A regular pentagon is constructible using a compass and straight edge, either by inscribing one in a given circle or constructing one on a given edge. This process was described by Euclid in his Elements circa 300 BC, simply using a protractor. A direct method using degrees follows. Draw a circle and choose a point to be the pentagons. Choose a point A on the circle that will serve as one vertex of the pentagon. Draw a line through O and A. Draw a guideline through it and the circle's center. Draw lines at 54 degrees intersecting the pentagon's point. Where those intersect the circle, draw lines at 18 degrees. Join where they intersect the circle. After forming a regular convex pentagon, if one joins the non-adjacent corners, one obtains a pentagram, with a smaller regular pentagon in the center. Or if one extends the sides until the non-adjacent sides meet, one obtains a larger pentagram. The accuracy of this method depends on the accuracy of the protractor used to measure the angles. Physical methods. A regular pentagon may be created from just a strip of paper by tying an overhand knot into the strip and carefully flattening the knot by pulling the ends of the paper strip. Folding one of the ends back over the pentagon will reveal a pentagram when backlit. Construct a regular hexagon on stiff paper or card. Crease along the three diameters between opposite vertices. Cut from one vertex to the center to make an equilateral triangular flap. Fix this flap underneath its neighbor to make a pentagonal pyramid. The base of the pyramid is a regular pentagon. Symmetry. The regular pentagon has DIH5 symmetry, order 10. Since 5 is a prime number, there is one subgroup with dihedral symmetry, DIH1, and two cyclic group symmetries, Z5 and Z1. These four symmetries can be seen in four distinct symmetries on the pentagon. John Conway labels these by a letter and group order. Full symmetry of the regular form is R10 and no symmetry is labeled A1. The dihedral symmetries are divided depending on whether they pass through vertices or edges, and O and reflection lines pass through both edges and vertices. Cyclic symmetries in the middle column are labeled as G for their central gyration orders. Each subgroup symmetry allows one or more degrees of freedom for irregular forms. Only the G5 subgroup has no degrees of freedom but can be seen as directed edges. Cyclic pentagons. A cyclic pentagon is one for which a circle called the circumcircle goes through all 5 vertices. The regular pentagon is an example of a cyclic pentagon. The area of a cyclic pentagon, whether regular or not, can be expressed as 1/4 the square root of one of the roots of a septic equation whose coefficients are functions of the sides of the pentagon. There exist cyclic pentagons with rational sides and rational area. These are called Robbins pentagons. In a Robbins pentagon, either all diagonals are rational or all are irrational, and it is conjectured that all the diagonals must be rational. General convex pentagons. For all convex pentagons, the sum of the squares of the diagonals is less than 3 times the sum of the squares of the sides. Graphs. The K5 complete graph is often drawn as a regular pentagon with all 10 edges connected. This graph also represents an orthographic projection of the 5 vertices and 10 edges of the 5 cell. The rectified 5 cell, with vertices at the mid-edges of the 5 cell, is projected inside a pentagon. Examples of pentagons. Plant's pentagonal cross-section of okra. Morning glories, like many other flowers, have a pentagonal shape. The gynoecium of an apple contains 5 carpels, arranged in a 5-pointed star. Star fruit is another fruit with 5-fold symmetry. Animals a sea star. Many echinoderms have 5-fold radial symmetry. An illustration of brittle stars, also echinoderms with a pentagonal shape. Artificial. The Pentagon, headquarters of the United States Department of Defense. Home plate of a baseball field. Pentagons in tiling. A regular pentagon cannot appear in any tiling. First, to prove a pentagon cannot form a regular tiling, observe that 360 degrees, 108 degrees equals 31/3, which is not a whole number, hence there exists no integer number of pentagons sharing a single vertex and leaving no gaps between them. More difficult is proving a pentagon cannot be in any edge-to-edge tiling made by regular polygons. There are no combinations of regular polygons with 4 or more meeting at a vertex that contain a pentagon. For combinations with 3, if 3 polygons meet at a vertex and one has an odd number of sides, the other 2 must be congruent. The reason for this is that the polygons that touch the edges of the pentagon must alternate around the pentagon, which is impossible because of the pentagon's odd number of sides. For the pentagon, this results in a polygon whose angles are all 2 equals 126 degrees. To find the number of sides this polygon has, the result is 360 equals 62/3, which is not a whole number. Therefore, a pentagon cannot appear in any tiling made by regular polygons. There are 15 classes of pentagons that can monohedrally tile the plane. None of the pentagons have any symmetry in general, although some have special cases with mirror symmetry. Pentagons in polyhedra.